Hey, I'm Simeon, and this week I came across a paper that I genuinely found interesting. Scientists just caught a black hole doing something we've never actually been able to prove before, physically throwing dust out of its own galaxy. Not gas, not light, actual dust. Tiny solid particles being launched across hundreds of thousands of light years by a black hole. And the reason this is such a big deal isn't just the image of a black hole hurling dust around, it's what that dust is. It's the same stuff that stars are made from. So if a black hole is throwing it out of the galaxy, those are stars that will never be born. Let me walk you through what they found and why it took this long to prove. So, first, a bit of context. Most large galaxies, including our own Milky Way, have a supermassive black hole sitting right at their center. We're talking about objects millions or even billions of times more massive than our Sun, compressed into a region smaller than our solar system. Most of the time, these black holes are relatively quiet, but sometimes they start actively feeding, pulling in enormous amounts of gas and dust from the surrounding galaxy. And when that happens, something interesting occurs. The material falling in doesn't just disappear quietly. It gets superheated, it glows incredibly bright, and it releases so much energy that it drives powerful winds outward, blasting material away from the black hole in all directions. We call a black hole in this active feeding state an active galactic nucleus, or AGN for short. And the winds it produces, which we call outflows, can actually affect the entire galaxy surrounding it. Here's why that matters. Galaxies form stars by collapsing clouds of gas and dust. That's the raw material. But if the black hole is blasting powerful winds outward, those winds up can heat up the gas, push it away, and essentially cut off the galaxy's ability to form new stars. We actually think this is one of the main reasons some galaxies just stop. They go from being these vibrant star forming spirals to being quiet, dead ellipticals over billions of years. The black hole at their center basically switched off the star factory. Now, astronomers have known for a while that these outflows are made of hot gas. But there's always been a question. Is there also dust in those outflows? And if so, is it being carried along or is it just sitting nearby getting heated by the radiation? This new paper answers that question for the first time. So, if we suspected dust might be in these outflows, why hadn't anyone confirmed it before? The answer comes down to a measurement problem that's surprisingly tricky. The way astronomers normally measure whether something is moving and how fast is by looking at the light it emits. When an object moves toward you, its light gets compressed slightly, shifting toward the blue end of the spectrum. When it moves away, the light stretches toward the red. It's the same principle as how an ambulance siren sounds higher pitched as it approaches and lower as it drives away, just with light instead of sound. For gas, this works beautifully. Gas emits very sharp, narrow lines of light at very specific wavelengths, so even a tiny shift is easy to detect. Dust is a completely different story. The specific type of dust this paper focuses on, tiny carbon particles called PAH, which stands for polycyclic aromatic hydrocarbons, basically microscopic flakes of carbon. These emit very broad, smeared out signals in the infrared. Not sharp lines, but wide, fuzzy humps. And the problem is that the velocity shift you'd expect from dust moving in an outflow is tiny compared to how wide those humps already are. It's like trying to hear someone whisper while standing next to a jet engine. The signal is completely buried in the noise. Previous attempts to measure dust velocity just couldn't cut through it. until this team tried a completely different approach. The technique they used is called PCA tomography. PCA stands for Principal Component Analysis, and you don't need to worry about the full name. The idea behind it is quite intuitive. Instead of looking at each individual point in the image and trying to measure its velocity separately, which is where the jet engine problem kills you, this method looks at the entire image all at once and asks, what patterns of variation exist across the whole thing? The first pattern it finds is the dominant one, the average dust signal from the whole galaxy, not moving. That's your reference point. The second pattern captures what's left over after you account for that average. And if the dust is actually moving, coming towards us on one side of the black hole and moving away on the other side, that motion shows up as a very specific pattern in the second component. Blue glow on one side, red glow on the other. Here's an analogy that might help. Imagine you're trying to spot a single person in a crowd who's waving their arms. If you look at any one person individually, you can't tell who's waving. But if you look at the pattern of movement across the whole crowd and subtract all the random noise, the person waving their arms stands out immediately. That's essentially what this technique does. It uses the collective information from every point in the image to extract a signal that no single point could reveal on its own. And it works. The team applied this to 10 nearby galaxies, all with actively feeding black holes, all observed with the James Webb Space Telescope, which can see in the infrared with extraordinary sensitivity and detail. For each galaxy, they mapped the velocity, the motion, of several different things simultaneously. The hot gas around the black hole, the cooler molecular gas further out, and the dust at 3 different particle sizes. Now, here's where it gets really interesting. The smallest dust particles, the tiniest carbon flakes, only show one thing in every single galaxy: rotation. The galaxy spinning, nothing more. No sign of being launched outward. But the larger dust particles tell a completely different story in 2 of the galaxies. Their velocity map doesn't look like rotation anymore. It's rotated. It's aligned with the outflow direction, exactly matching the hot gas being blasted out by the black hole. Those larger dust particles are moving with the outflow. And the reason the small ones aren't? Well, they don't survive long enough to escape. The radiation pouring out of the actively feeding black hole is so intense that it destroys the smaller, more fragile dust particles before they can get carried away. Only the larger, tougher ones make it out. So we're not just seeing dust in the outflow. We're seeing the specific dust that survived a brutal radiation environment it got launched. That's a remarkable level of detail. Now at this point you might be wondering, okay, but how do you know that the velocity pattern isn't just the galaxy rotating in some complicated way? How do you rule out that it's just an oddly shaped disk? That's exactly what the researchers asked themselves. So they did something careful. They built a model of what the galaxy's rotation should look like, using everything already known about the galaxy's shape and orientation from previous observations. And they subtracted that model from what they actually measured. Think of it like subtracting the background music from a recording just to hear the vocals. Once the rotation is removed, what's left should be purely the outflow. And what's left matches the hot gas outflow almost perfectly. Same direction, same structure. Blue dust moving towards us on one side, red dust moving away on the other, along the exact same axis as the black hole's outflow. The dust is in the outflow, that's confirmed. One detail I kept coming back to, in one of the galaxies, NGC 7582, The dust outflow component is actually stronger than the molecular gas outflow. The dust is the dominant thing being thrown out. I didn't expect that at all. There's one more thing worth looking at here: how the dust actually moves through the outflow compared to the gas. Both follow the same general pattern. They speed up as they get pushed away from the black hole, then gradually slow down as they sweep up material from the surrounding galaxy, like a snowplow piling up more and more snow. But the dust speeds up faster and slows down earlier than the gas. The dust hits its peak speed much closer to the black hole and then drops off. Why? Because dust particles, especially these tiny flat carbon flakes, have an enormous surface area relative to their weight. A light pushes on surfaces, so the radiation from the black hole can shove dust around very efficiently. Like how a solar sail works, using light pressure to move a spacecraft. But that same large surface also means the dust runs into more resistance as it plows through surrounding material, and it slows down faster. There's also probably a destruction effect happening. As dust particles accelerate to very high speeds, collisions become violent enough to shatter them. So the fast-moving grains may simply not exist anymore at larger distances. They've been smashed apart. Only the slower ones survive to reach the outer parts of the outflow. One last question worth addressing: where is all this dust coming from in the first place? You might think it's being launched directly from right around the black hole, from the ring of gas and dust that immediately surrounds it. But the outflows detected in this paper are happening thousands of light years away from the nucleus. The material immediately around the black hole is much closer than that. So the answer is that the black hole's outflow is acting like a pressure wave pushing outward through the galaxy. And as it moves, it sweeps up and carries along dust that was already distributed throughout the galaxy's interior. Dust just sitting there in interstellar space, minding its own business, that suddenly gets picked up and thrown outward. The black hole isn't launching its own dust. It's grabbing the galaxy's dust and throwing it out. So let's zoom out. What does this actually mean? For decades, scientists have modeled black hole outflows as being made of gas. That's what the models assumed, and that's what most of the evidence pointed to. Dust was a bit of a mystery, though. It showed up near these active black holes in images, but we didn't know if it was genuinely part of the outflow or just a bystander. This paper shows that it's not a bystander. It's an active participant. And that changes the calculation for how much material a black hole outflow is actually removing from a galaxy. Remember what dust is. It's the raw ingredient for stars. When dust collapses under gravity with gas, stars form. So when a black hole launches dust out of a galaxy, it isn't just heating the environment and making it harder to form stars. It's physically removing the material those stars would have been made from. Those stars simply won't exist. It's a more direct, more physical way for a black hole to shape the fate of its own galaxy than we appreciated before. And none of this would have been visible without the James Webb Space Telescope. Previous telescopes couldn't do this measurement. The infrared sensitivity and the spatial resolution just weren't there. JWST made it possible. And I suspect this is the first of many results like this. A black hole at the center of a galaxy far away, quietly reaching out and throwing the building blocks of stars into the void. Not as a side effect, but as a mechanism, as part of how galaxies slowly go dark. We just watched it happen for the first time. The paper is linked in the description if you want to read it yourself. It's genuinely accessible for a scientific paper. And if this is the kind of thing you're into, I'd love to hear what you think in the comments. I'll see you in the next one.